because we had to stop rather abruptly our graphing last time, I thought we'd start with a little supplemental activity. So I've given you that. If you are online, there's a module that says supplemental activity printed out. So this is just another exponential graph like the last one we did at the end of last session to warm you up. So I'm going to give you a couple minutes to graph 1/3 to the x power, answer those questions at the bottom just as a reminder, and that kind of gets us caught up with whereabouts in section 6.2 we left off last time. Warming up for the back right here. You're welcome. Now it's nice to remember the general shape of our exponential graphs. Where we left off last time is when the base here, which in this case is 1/3, when that base is greater than 1, then you're going to get an increasing graph. When that base is between 0 and 1, as this one is, you're going to get a decreasing graph. So that's good to remember. And then the amount of increase, decrease is just dependent on what the base is. So I'm going to go ahead, I'm going to plug in some x values. We're going to see what the y values are. You're welcome to plug in whatever you want. You probably plugged in a whole bunch of different values. I'm going to plug in these -2, -1, 0, and 1. And I picked those because those are what's going to fit nicely on my graph right here. And so just showing you the work, when I put in -2, I've got 1/3 to the -2 power. Well, remember that negative in the exponent flips our base. So this becomes 3 over 1 to the 2 power, which is 9. Same thing for -1 when I have 1/3 to the -1. Again, the negative flips the base, so I get 3 to the first power, which we would just write as 3. Anything to the 0 power is going to be 1. And then 1/3 to the first power, well, 1/3 to the first power is just 1/3. So those are going to be the 4 points that are best for us. Now I'm going to plot those. -2, I go up 9. Here's a nice dot. -1, I go up 3, 0, 1, 1 and a third. And if you put in 2, then you got a 9th. And all that's indicative there is that it's just going to get closer and closer and closer to the x-axis. Remember that the x-axis for our basic exponential graph is an asymptote. Okay, so we don't want that graph to go through the x-axis. Also, be careful when you draw this for me on a test. You don't want to then bounce off the x-axis and come back up. It does not do that either. Okay, so it's just a continually decreasing graph. So my domain, the domain of any of my exponential functions is -infinity to infinity. I can plug in any x value left and right and raise something to a power. The range, well, the range of this one, since it's just my basic, is above 0. 0 is the boundary, but it's never going to equal 0, so I'll put a parenthesis there. And then it continues to go up and up and up to infinity. Is this function increasing or decreasing? Well, my y values, as I trace it from left to right, my y values continue to get smaller and smaller. So this one's decreasing. And one of the last things I said, and I know we were a little hurried at the end, the reason this is decreasing is the value of my base, which we call A. Our book uses the letter A, although it doesn't matter. The value of A is between 1 and 0. And so that's when it's decreasing. So any fraction like a fourth or 2/3 or 5/8 would give you a decreasing graph. It's increasing, in case you don't remember, it's increasing if the value of A is greater than 1. Now, when we're considering exponential graphs, we do not consider the case where A equals 1 because 1 to any power is just 1 and it's just a constant function. It's not very interesting. So in fact, when we defined, or at some point we might define the exponential or the next function, and we'll see that. And last but not least, just to tie this together with what we did in our first section, is this function 1-to-1? And the answer is, how do you know from the graph that it is 1-to-1? Because of the horizontal line test. Beautiful, love it. Thank you for remembering. Yes, because of the horizontal line test. Excellent work. And if you remember, the reason that we cared, and if we get to start section 6.3 today, which I think we will, we're going to see how that materializes here. So that is our supplemental review activity to get us warmed up. Does anyone have any questions up till this point? I think if I'm scanning the crowd, I think everyone was here last time. So your front page of your 6.2 sheet should be complete. If you need another one, I have a few extras up at the front. The reason I mention it is because the next page is going to be based on these graphs. Okay, so when we go to page 2, the first thing we're going to be asked to do is graph 2 to the x power minus 4. Again, all I'm doing here is reminding you of the transformations that we've been doing all semester and how they look with our exponential graph. So I'm going to give you 60 or 75 seconds. You can reproduce 2 to the x power if you need to from the front page, and then what is 2 to the x minus 4? does this minus 4 right here do to my basic graph of 2 to the x power? Brings it down 4. It is external to the function. It's not attached to the x, so that is doing something to my y value. So it's going to bring the whole graph down 4. What I'm going to do first, since it is a vertical translation, is I'm going to take the horizontal asymptote and I'm going to drop it down to -4. That way I know where my landing strip is for my curve. And now I'm just going to drop all of these points down 4. So my rightmost point, which has a y value of 8, when I descend 4, goes to 4. The next one, which has a y value of 4, goes to 0. The next one, which is a y value of 2, goes down to -2. The next one, which has a y value of 1, goes down to -3. And last but not least, this point, which has a y value of 1/2, goes down to -3.5. And there's my points. So purple is the answer to this problem. Remember, our translations do not change the shape of the graph at all. They just change its position. And we just slid that graph down 4. Anybody got a question, comment, or concern? These skills are a review, but we're applying them in a new context. So if there's anything that this drums up, a question, comment, concern, let me know. The next example 4, if I go down to the next one, again is based on one of the graphs from the front page, the 3 to the x graph. So you can look back there at the basic points we had, and now do 3 to the x minus 2 power. All right, this time the -2 is up here with the x. What is that going to do to my original graph? It's going to move the whole thing to the right, the positive x direction too. So in pencil, I've just reproduced the 3 to the x graph from the previous page. So I'm just going to take that graph and I'm going to move the whole thing right too. I'm going to remind myself that the x-axis is going to stay the asymptote because I've not moved this up or down at all. And so now when I take this first point, which is at an x value of 2, it goes over to an x value of 4. The next one's an x value of 1. It goes over to an x value of 3. This one's an x value of 0. It moves over to 2. And lastly, this is an x value of -1, and it moves over to +1. So again, the shape of my graph is the same. It has just been moved to the right 2 units. I'm going to assume, unless somebody asks a question, that there's not one, so feel free to ask it. And then the last of our translations, again, based on one of our previous problems, is a -1/2 x. the negative being out in front of this graph, what does that do to the graph? It flips it because it makes all of what values negative? The y values. Since it's out in front of everything, it makes all the y values negative. Yes. So this first y value on the left is positive 8. Now it becomes negative 8. The next one is positive 4, becomes negative 4. Positive 2 becomes negative 2. Positive 1 becomes negative 1. And positive a half becomes negative a half. Once again, my horizontal asymptote is not going to change on this graph because we've not raised it up or down. And here's my graph. It's just been reflected about the x-axis. So once again, there's not really anything new per se in those problems. We've been talking about transformations every time we come up with a new graph. Now it's just the transformations on this exponential graph. Before I flip the page to the last bit for this section, is there a question about anything we've done? Please feel free. I love questions. All right, so the last thing that we are going to do in this section, since we have a new type of function, we are going to look at equations involving that function. And we're going to do this twice, once in this section and once in the last section of this particular unit. So right now, we have what our book, because it's very clever, calls type 1 exponential equations. And that really tells you nothing about what we have. So a better description of the first type of exponential equations that we're talking about are equations where we can equate the bases. So what is being referred to as a type 1 exponential equation is an equation where you can make the base on both sides of the equal sign into the same thing. If you can't make the base into the same thing, then that's what's called a type 2. Again, not very descriptive, but there's a different method to be able to do that, and we will talk about that in our last section of this unit. So my first problem here asks me to solve this. 25 to the x power equals 125. And since the x being in the power is new to this section, I don't have any ability to get the x out of the power. Multiplying and dividing both sides doesn't do anything. Square roots, none of that is going to work for me. So I'm going to make the base the same. 25 and 125, they are both based on what numeric base? 5. I can write both of these as some power of 5. In fact, I'm going to do the right side first since there's no variable. And if you need to use your calculator, that's fine. That's why you're allowed to use your calculator. 125 is 5 to what power? 3. 5 times 5 is 25. 25 times another 5 is 125. So 125 is 5 to the 3rd power. And again, your calculator can tell you that. So please don't stress over that. Grab your scientific calculator and just hit some 5s and see how many it takes. On the other side, the 25 can be written as 5 to what power? Squared, 2. So here's what I'm going to do. I've got 5 to the 2nd, and then that's being raised to the x power. Now, by the power rule, since I have 5 to the 2nd raised to the x power, when I have a power raised directly to another power, what do I do with these two exponents? I multiply them. Don't add them. Let me just do a quick little review. So here are the two properties of exponents that we're concerned with in this problem. For instance, if I have x to the 2nd power times x to the 5th power, when I am multiplying the bases, that's when you add the exponent. So that's x to the 2 plus 5 power, or 7. If I have x to the 2nd raised to the 5th, so notice the difference between the two things. This is a power raised directly to another power. That's x to the 2 times 5, or 10. So in this particular situation, I have 5 to the 2nd raised to the x. So that becomes 5 to the 2x power equals 5 to the third. And here's the nice thing about exponential functions. Since they are 1 to 1, okay, since every input gives exactly one output, and if they're all different, since I'm saying 5 to this power on the left is equal to 5 to this power on the right, what that means then is that the powers have to be equal. This can only be true only if this is true. So 5 to the 2x can only be equal to 5 to the third if 2x is equal to 3, if the powers are the same. And if you need a justification, if you're taking notes, the justification for that is that's a property of a one-to-one function. Now it becomes something that we can all solve in our sleep. I'm going to divide this by 2 on both sides, and I get x is 3/2. Since the domain of an exponential function is all real numbers, then I know that that is going to be a just fine solution. You're welcome to check it in your calculator. It's totally a good thing to do when you're taking the test to know that you've got it right. So there is the essence of solving a type 1 exponential equation, meaning an exponential equation that you can make the bases on both sides the same. So I invite you to do the same thing for exercise 6. You've got 4 to the x plus 1 power is equal to 8. It's a super similar problem to what we just did. Just to give everybody a little nudge in case you're staring at the problem not knowing what to do next, what is the base that you can write 4 and 8 as a power of? 2. Yes, so that should be step 1, writing the 4 and the 8 as a power of 2. And let's see how you did on this first one, and then I'll give you a little more time on the next one. So you just told me a moment ago that I can write 4 and 8 as a power of 2. So 4 can be written as 2 to the second power. And then 8 can be written as 2 to the third power. Like I said, this is super similar to the previous problem. Instead of the base being 5, the base is 2. Same powers. Now, on the left side of this, again, here is the power rule of exponents. I have 2 to the second power raised to the x plus 1. What do I do with those two things? Yes, so just don't forget to distribute. We have to multiply them. So 2 times x plus 1 gives me 2x plus 2. Most common mistake students make is to write 2x plus 1 there. So please don't forget to distribute. Now I'm going to finish the problem. I'm going to subtract 2 from both sides and get 2x is equal to 1. Divide both sides by 2, and I get x is 1/2. And so that is my solution set. The value of x is equal to 1/2. Anything we have to get out in the open before I have you do the next problem? All right, exercise 7. Again, it's essentially the same thing, just different numbers. Give it a go. 27 and 9 can both be written as powers of what base? 3. Okay, so 27 is 3 to the 3rd power. And then 9 is 3 to the 2nd power. Now, you don't have to write the things in parentheses. If you are fully adept at doing the multiplying right away, skip that step if you're capable of it. But if that's a stumbling block, then just write it down. It only takes a second. On the left side now, 3 times 4x is I've got 3 to the 12x. On the right, I have to remember to distribute, so I have 3 to the 2x plus 4. So again, those two things can only be equal if the powers are equal. So 12x has to equal 2x plus 4. I'm going to subtract the 2x from both sides, and when I do that, I get 10x on the left and 4 on the right. Now I'm going to divide both sides by 10, and I get x is 4 over 10. That's not a reduced fraction, so I'm going to reduce it. That is 2 over 5, or 0.4 if you're a fan of decimals. Doesn't matter to me. So there we go. 2 over 5 is the solution to that problem. I've got one more. Okay, this now involves having a fraction, so hopefully you remember from the, oh, hey, a hand, what's up?
Yeah. What would happen if you try to plug it in to make sure they're equal? Like, do you guess and check it? Because I tried to plug it in. I don't know if I did it wrong, but I got like 2 different answers on one for the, whenever you plug in 2/5 for the x.
Okay, so what you're finding out is it becomes a number that you can't do in your head. So what I would say is that's when involve your calculator in helping you find the solution. So on the, let's double check this and make sure we've done our work right and see what's going on. So the question, if you're watching this on video, is we've substituted the 2/5 in and we don't feel like we're getting the right thing. So what I've got on the left is 27 to the 4 times 2/5. And on the other side, I have 9 to the 2/5 plus 2. Now we can use 2/5 as 0.4. Probably makes this a little bit easier. So on the left, we have 27 to the 4 times 0.4, or 1.6. On the right, we have 9 to the 2.4. And now I'm just going to rumble into my calculator, and I'm going to see what those are. So I didn't bring a calculator, so let's see how the Google or the Apple calculator does for me here. So 27, we're going to raise that to the 1.6 power, and we get 195.066 and some change. So we'll have to remember that. And then I've got 9 to the 2, whoops, that's the wrong button. Let's try again, 2.4 power. and I get 195.066. Okay, so did that answer your question? Are we good?
Yes.
Awesome. Appreciate it. Love it. Sorry I didn't see you. The monitor was in my way when I looked at my peripheral vision. Are there any other questions? That's a great one. Yeah. The way you would know, the question is if the two sides aren't equal, which you have empty set, in general, if you come up with a number value, it's going to work unless something weird is going on in the exponents. The way you would know you have a problem with the empty set is if you ended up with something like x plus 4 is equal to x minus 5. So then what happens is the x's cancel on both sides and I end up with a contradiction. And so then I'd have an empty set. So as we've seen in previous equations, great questions, both of you. I appreciate both of those. So finish up with equating the bases here of exercise 8 and seeing how it goes. So the gimmick to this problem, and the reason I had you do it, is I wanted to involve at least one with fractions to remind us of that. And as we saw when we were graphing, when my base is in the denominator, that means the exponent is going to be what? A negative. So what you would probably notice is that 1/2 and 16 can both be written with a base of 2. So 1/2 is 2 to the -1 power. Now that's difficult. If you didn't quite see that, that's okay. That's why we do these examples in class, is to help you out with these things. On the other side, 16 is 2 to the 4th power. So notice what I'm trying to do in every one of these problems is I'm trying to equate the bases on both sides. And so both of these bases can be written as 2. The 1/2 is 2 to the -1. The 16 is 2 to the 4th. Everybody with me now? I know that might have been hard to discern before we did an example. The rest of this is just like what we've done. So now I'm going to distribute. So on the left, I get 2 to the -3 plus x power. On the right, I get 2 to the 4x plus 8 power. Both of those things can only be equal if the powers are equal. So I've got -3 plus x is equal to 4x plus 8. I'm going to put all of my x's on the left, so I'm going to subtract the 4x to get it over here. When I do that, I have -3x. Then I'm going to add the 3 to get all the 3's over on the other side, and I get 11. And when I divide both sides by -3, I get -11 thirds. So there it is. There's my solution. That would make both of those equal.